So I would like to present this current work of mine and Shannon. We are working together on something that is called clip effect suppression for correlated multiple description coding. So before introducing the notion of clip effect, which is a fairly loaded term, a bit more rigorously, I'm going to define it as part of a phenomenology which is video delivery over heterogeneous networks. So this is at the same time motivation, immediate motivation for this work. So nowadays we are facing proliferation of heterogeneous video devices with different screen resolutions, different processing capabilities, different screen profiles, and also we have heterogeneous networks, different channels that all those devices use. A state-of-the-art solution to the problem of heterogeneous video delivery is called Scalable Video Coding, or SVC, which is part of state-of-the-art standard for video compression, H.264, where you practically have some estimate of the channel, you know the channel capacity, and according to that, you do compression of your video source so that it's compressed into a bit stream that can be accommodated by the channel. So the bit rate of this bit stream obviously needs to be smaller than the channel that you have. As a result, you can, also before that, but that's the usual approach. In scalable video coding, you have the application of so-called multi-layer source coding, where you have several self-sufficient layers of code, and you can, at the destination, extract the basic layer or basic layer plus enhancement, or you can get the full gear. As a result, you have the video reconstruction of several resolutions, either the low quality or the full low quality or low profile. So that's the current state of the art. However, if you have a lossy network where you can easily use the basic layer, you cannot reconstruct the higher layers. So there's only a certain order in which you receive this encoded bit stream where you can actually achieve such a graceful degradation of the video source from the highest to the basic level of quality. I hope everybody knows what I mean when I say lossy networks, and internet network practically is a lossy. Okay, so let me just summarize traditional video coding, several varieties of that. For point-to-point channels, as I already described, you have a video source that you just compress so that it can be accommodated by the known channel, or at least some statistical channel that doesn't have to be fixed, whose capacity you know, and so you can channel code to achieve that capacity. And as a result, whatever you receive, you can reconstruct it to something close to the original signal. When you don't have point-to-point channels, and that's always in so-called network information theoretic channels, such as broadcast channel, parallel channels, multiple access channel, and so on, or temporally varying channel that can also be modeled as a parallel channel, for example. So for those channels that are not point-to-point channels, things like this may happen. So you make an estimate regarding the channel capacity, and you compress the source according to that. However, your channel underperforms, so your estimate was not good enough, and as a result, because this bit stream is not self-sufficient, you cannot reconstruct anything, so you get practically a black screen. You can apply the scalable video coding. So
you're saying that's the case for you code for one channel and channel's worse than...
Exactly. You effectively miss the estimate, channel estimate. Or you can be smarter, you can model your channel better, and you can assume that there is some varying, the channel is of varying quality, and so you decide to compress on multiple layers, where when you compress to the basic layer, then you get a bit stream that is self-sufficient, and then you can reconstruct from that and get some lower quality signal, but at least for the purpose of reconnaissance, for example, you can use that. So you actually have some sort of graceful degradation of the video quality. However, you know, if the channel further deteriorates, you again get nothing. So it's like a never-ending war with the channel. Okay, so now I would like to introduce the cliff effect, which I illustrated in this in the fact that when the channel changes with respect to what we estimated, we cannot reconstruct the signal. And here it is illustrated by this curve, where, for example, if we do the source compression according to some estimated channel of quality SNR asterisk, and the channel turns to be worse than that, then our distortion is maximal. We don't get anything. And also, if the channel gets better with respect to estimated channel, we don't get any improvement with respect to the reconstruction quality, which is popularly known as the cliff effect. However, cliff effect is inherent to digital communications, and as it says here, it is essentially the consequence of Shannon's channel capacity theory. So if you compress a source to rates that are smaller than the capacity, then your transmission can be made virtually error-free. If you compress it to a rate that is larger than the channel capacity, the error probability goes to 1 exponentially fast with the message line. But the problem here is more about being able to estimate the channel capacity to properly model your channel, which is getting increasingly difficult, more and more difficult for heterogeneous networks. Also, in the state-of-the-art video coding, which I mentioned previously, you actually don't have any mechanism to control your rate versus the quality of your signal. So I'm going to say a little bit more about that later. Okay, so this is, as I said, not evident in classical video transmission schemes related to point-to-point communication, but it is existent in the discrete networks. Just wanted to mention that some data is more sensitive to channel quality variations, especially video data, and that's why it's an immediate problem, very popular nowadays, because of a lot of correlation memory in the video signal. So you actually cannot extract a pixel of video that has some semantic meaning, and if you get it, that it actually causes some perceptual increased quality, perceptually increased quality.
Silvija, are you kind of thinking about like internet and packets being lost, or are you thinking about wireless channels, or both?
Both. I'm thinking in terms of SNR, but I'm also thinking in terms of lost networks, where whatever you compressed, you put into a packet, but then you lost that packet, or packet gets delayed to the point that at a time of real-time playing, it's not available. So it's pretty much the same. So for delay constrained applications in a video, it is very important. So okay, so where I am. So this is just another illustration taken from the Softcast presentation at MIT. This is one of the practical approaches to cliff effect, where here there is an example of if you compress your source, for example, to 54 megabits per second, expecting a channel of quality somewhere above 20 dB. But you know, the channel kind of underperforms, you get nothing. The same if you expect the channel to be around 2 dB, but you know, the estimate is not good enough. So the problem here is actually knowing the channel exactly what it would be and source coding for that channel so that you get the best performance. It's either the best performance or nothing. So just a couple of current approaches to cliff effect mitigation. One is the application layer, where you simply send a couple of unicasts to different devices that experience different channels and that have different requirements. Of course, with the temporarily varying channel, it doesn't work, and it doesn't work in terms of resource consumption, because you have bandwidth, high bandwidth overhead, latency, congestion problems, and so on. At the channel coding level, state of the art is in 3GPP to use hybrid ARQ, so that you are chasing your channel quality. If the channel is not good enough, then you have the selective feedback to increase the forward error correction strength. But obviously, because of the feedback, it does not work for wireless broadcast, and it doesn't work for any multi-terminal communication. At the source coding level, there are two approaches. One is multi-resolution coding, which I already illustrated on the example of scalable video coding, where you have one base layer and multiple refinement layers. In lossy networks, as I mentioned, we don't achieve graceful degradation with that, because if you don't receive the basic level, you cannot reconstruct anything. So only a certain order of received layers work. Another approach is multiple description coding, and the reason it's in red here is because our approach is going to be partially based on that, where any additional description improves quality. But the problem is to actually quantify how much it is improved with each new one. It does work, obviously, in lossy networks, because every description of the source is equal. Finally, source channel coding approach, or source approach with the channel in mind, as it's popularly called. Here's a reference here. It's a seminal paper that uses some codes similar to MDS codes, where graceful degradation is achieved above certain point of channel SNRs, but not before that. As opposed to that, our goal is to achieve graceful degradation for the whole range of channel qualities of interest. And finally, I'm mentioning here two practical source channel encoding methods. One is softcast. I had a slide previously based on that approach, actually illustrating cliff effect, developed at MIT at Tina Katavi's lab, and smooth streaming, which is a Microsoft approach. For softcast, it is practically an amplitude modulation, but authors don't describe it like that. So practically every single constellation point is differently modulated, and the modulation gain needs to be sent in terms of some metadata. And because of that, there's an excessive bandwidth consumption. So it's sort of, you are mitigating cliff effect because you're jumping to analog transmission instead of digital, but at a certain cost. Another approach is smooth streaming by Microsoft, where what they do, they actually encode the video source into several resolutions. And they put all those different versions of the video content somewhere in the network storage in the cloud. And when the destination is receiving the data, it starts with some projected estimated quality resolution according to the channel expectations, but then based on the measurement, the feedback is constantly being sent to a manager of this video transaction. And so if the channel is bad at the destination, then the continuation of this streaming is transferred to another version of lower quality. So practically there's a lot of scheduling and alignment involved with that, and obviously a lot of feedback. So it's not very efficient in terms of any resource. Okay, so what is our goal? If you remember, this is the slide that I borrowed from Softcast MIT that illustrates when you encode for various qualities, embed for various qualities, and you experience the cliff effect for the matching channel. So if the point-to-point channel state-of-the-art coding is very close to optimal, which it is, and we take that these are actually points on the theoretical performance bound. This would be the theoretical rate distortion bound. So the optimal term that connects the rate to the source quality or source distortion. This is state of the art, very, very close to that. But it is point-wise. So if you achieve the optimal distortion for a certain rate, you can achieve it only for that rate. You go below that, you don't get anything. So in order to achieve scalability, we would need to be somewhere here. Whether it's a parallel line or it's somehow slanted, how it depends on the channel quality, we actually don't know. How it depends on rate. So we would like to quantify that. What do we have to trade off for the scalability? No existing approach, including state-of-the-art SVC, compressive sensing, soft gas, smooth streaming, quantifies the gap to theoretical limits and the necessary trade-offs. So our first goal is to do that and to find a constructive way so that we can demonstrate this. Here I'm just summarizing those goals. So we would like to create a scheme with acceptable performance in a range of network conditions, practically graceful degradation, signal quality, and channel deterioration. We would like to come up with a scheme that is implementable, as opposed to typicality based on constructive schemes such as used in information theory. Also, as I said in the previous slide, we would like to quantify the gap with respect to the non-theoretical performance limits.
So Silvija, is this the PSNR kind of metric for video quality?
PSNR is a commonly accepted metric, but it's not very well. It's practically a dB of it's a logarithmic scale of signal strength versus noise strength.
Yeah, like for instance, like you have choices in here that in terms of like simple things, you could choose to have lower frame rates, or if you don't have that choices, it always the frame rate is some number of frames per second.
Okay, so if you say, for now I'm going to concentrate on still pictures. And if you noticed in my illustrations, I didn't have 7 frames, I had still pictures, and if you reconstruct them, they have either some low quality or they have the right quality as the source. The difference with the different frame rates in video, if you take the time component into account.
Take the what?
Time component into account, it is not much bigger difference because of the high correlation between the objects in one picture and the next one. So the correlations are both within one picture at a single instant and at the second picture. So I can discuss that later after I introduce the scheme based on very simple sources. Because believe me, it's actually very, very complicated. That is the reason why we started from the scratch. And there's also a divide in the community, as you know. There are source coding people and channel coding people, and they even have different terminologies. So when somebody said we achieved the optimal quality in state-of-the-art video coding, that doesn't mean at what cost. I mean, it doesn't tell you at what cost. What is the rate for which you achieve that quality? In fact, what they are doing nowadays, they put the video signal to a linear transform, for example, DCT. And then at the output of that linear transform, where you expect to get some uncorrelated symbols, you put that through some big block where they do detection and estimation, and they try to find correlation between the points in the picture. For example, I don't know, this is correlated to this one, or I don't know, there's a wave, this is correlated to that one. And based on that, they only encode the differences between those highly correlated pictures. So that is done through that detection and estimation block in multiple passes until you are satisfied with the output of your DCT. So there's no exactness, there's no parameter that tells you, oh, okay, your desired rate was this and your desired distortion was that. It's just perceptual.
Is that how H.264 works?
Yeah, H.264 works exactly that way because encoder is not specified. It's sort of like magic, more art than...
But this, what you just described is per frame. What about interframe?
The same way. Intraframe, they also find correlation between the frames and do it the same way. Of course, it's more complicated because you have different IP frames, but in essence, the approach is completely the same. So you're trying to find so-called motion vectors. Motion vectors are actually sequences of highly correlated pixels. And once you identify those motion vectors, then you practically take the difference between those points and only encode the difference. Of course, you set the first pixel and then the difference with respect to the first pixel in that highly correlated motion vector that is described. But it's not strict in any way. So, but I think maybe it's, as I go with simple sources, try to explain that, it's going to become more clear.
I mean, the way you sort of explain it sounds like you take a block of frames and then you treat it as a block processor. But there must be, probably it's a time.
Yeah, there's a block of frames.
The time windowing.
There's a block of frames where you identify, for example, this can be a block of frames that are correlated. But also you're looking for a correlation within each block. So there are two axes on which you're trying to extract redundancies. And it actually boils down to the same mechanism, to identifying so-called motion vectors within one picture, still picture, and in between highly correlated pictures. Every now and then you get an independent frame. And then you start the same thing over and over. But as I said, it's more art than any rigorous science, because you are trying to extract this redundancy in multiple passes. And that's why there's now an initiative to create a new standard, because you cannot achieve within constraint delay, especially for 3D video, you cannot achieve the actual quality that is now required in new applications because of the multiple passes. So that's one of the motivations. I didn't want to go too deep into that, but obviously it's an interesting subject. So let me just go back to the basics, information theoretic basis. What is very important with respect to quantifying how far away we are from the theoretical bounds. So for point-to-point transmission, it is optimal to separate source and channel coding. We know that we take a source, some sequence of length L, then we encode that into some symbol, some code word from this set, and then we add redundancy, and then send it over the channel. So in source coding, we are removing the redundancy by mapping it to a smaller finite number of code words, and then and then in channel coding we are adding redundancy in a controlled way. So for point-to-point information, point-to-point communication, which is not our concern, this is the optimal way. You don't care, you do source coding the way you want, then you do channel coding. The optimality of separation does not always hold, as we illustrated many times here, for network channels. And here's just how some basic facts that are going to help us explain why. So, rate distortion is a function that gives the minimal mutual information per letter required to reproduce source X with average distortion D. So this is what I've been calling theoretical performance bound. For video, that would be, you know, with some hand waving, the number of bits per pixel resulting in average distortion D. However, you have to define distortion. Not every metric is good for every type of source. For binary source, it is usually Hamming distortion. For Gaussian source, it's minimum mean square error. And for video, as you have seen it's PSNR currently, but it's not optimal. So before defining the actual rate distortion function, we need to define the metric, the distortion metric. It's usually defined per symbol. It's obviously a metric that is always either 0 or positive, and it's 0 only if the reconstruction is equal to the source symbol. So this is so-called lossless coding, lossless source coding. Then we define, based on that, average distortion, which is then just an average over all possible signals and all possible letters in the reconstruction alphabet. So now we can define this rate distortion function, which is the minimum mutual information between reconstruction X from some alphabet, defined alphabet, can be the same as the alphabet for X, and the source random variable X. Given that the average distortion is smaller than this D asterisk. So what we define as to be an argument of this function is actually the threshold that we want to achieve in terms of the quality. So we're looking for the minimum mutual information between the source random variable and the reconstruction random variable, so that the distortion defined this way is smaller than some threshold. So there's a lower bound when this distortion, this is here also some less rigorous notation, is statistically independent from the source. Okay, what it means for some simple sources. This is for the binary symmetric source, which is Bernoulli 1/2, unbiased coin. It is known that the rate distortion function is 1 minus h of d. For those of you who know information theory, this is exactly the capacity of binary symmetric channel with cross error probability d. So we can actually achieve optimal compression for the uniform binary source, or binary symmetric source, by putting it through a binary symmetric channel of cross probability D. However, it's just an analytical box. how to in reality how to achieve that. It's a completely different question. So as a result, if we do that for any defined D here, which here we have the distortion. I apologize for not putting D here. So for any distortion that we pick here, D, we can optimally achieve it for the rate defined here, from 0 to 1 in terms of bits per channel use. Okay, so here you can just guess. That's the distortion of 0.5. You can just guess what you have at the source. And here, in order to know the binary symmetric source completely, you have to send the entropy of that source, which is
the top of that graph is just like they're essentially independent. The just guessing part.
Just guessing part, yeah.
They're essentially independent.
Yeah, because your rate is 0. You're just guessing. So your rate here is 1, and you are sending actually 1 minus h of 0. You don't have any uncertainty. Okay, so Gaussian source, also known rate-distortion function. This is the measure of this is the probability description, statistical description of the source. So variance is sigma squared of the Gaussian noise, and this is the distortion that we put as a threshold, as a constraint. It is here the distortion metric is defined as a minimum mean square error between the reconstruction x and the Gaussian random variable x at the source. The rate distortion curve looks similar to this one, although the distortion can be 1, and here it's 0.1. And you can actually analytically achieve it by adding some distortion noise, by adding some Gaussian variable with distortion noise omega z, and calculating that noise optimally so that you have minimum mean square error here for linear estimate. So it is implementable as an analytical model. Now I'm going to present you a multiple description approach for a binary symmetric source as presented in the previous slide, where we want to send description of that source over a channel of maximum capacity 1. That channel is quantized in a certain way into n channels of capacity 1 over n each. So why we do this quantization of the channel? It is practically decided based on the expectation of reconstructible of a meaningful reconstruction of binary source. So if you get a distortion that matches the rate below 1 over n, it doesn't have any meaning for you. So it's a matter of design, actually. And then each of those channels is somehow channel coding so that if you receive a description over that channel, it is errorless. You completely get it. Or you experience an erasure over that channel. So it's either 0 or 1.
The 1 over n is the minimum distortion you want to.
For 1 over n, this is minimum acceptable distortion in terms of our design. For example, if you would put a video source over that, the distortion that would match this rate would be unrecognizable perceptually. For example, it's a matter of design how you.
Is it maximum or minimum? Maximum distortion.
Would you repeat the question?
Is 1 over m the maximum distortion or the minimum distortion that you?
1 over m is not distortion, it's a rate.
Oh, the rate that corresponds to.
So rate,
The
in
minimum
terms
rate
of what I
corresponding to the
said,
maximum distortion.
yeah, so the rate is here. So we want that rate, and according to the optimal quantizer, for each of those channels, we are going to have Q of m designed as a binary symmetric channel with cross error probability d. This is how we create a description. And that description, having the rate 1 over n, can fully go over that channel unless the channel experiences an erasure. So the channel is either fully deterministic, so to say, or experiences an erasure. So this trick is actually is a quantization of the channel quality. We don't allow channel to go below that because to us it doesn't have any meaning. For example, perceptual. Okay, so what we do, we decide to create n equal descriptions of the channel, of the source. And since the source is binary symmetric source, we know how to optimally quantize or how to optimally describe that source in terms of rate-distortion curve. So, in other words, this is a binary symmetric channel with this crossover probability. So, but these descriptions are independent. So, these are different instances of the binary symmetric channel, so to say. Because of that, we expect that our error obtained with a collection, for example, of k different descriptions is going to decrease because these are the independent distortions. And so as a result, if we take a joint decoder, which is actually a majority logic decoder, we are going to get something that is better, certainly, than one description. So, okay, so here is, as I mentioned, for the majority logic decoding, the binary error. And this is the curve that we get if we are collecting more and more distortions. So let me explain this a bit. By the way, I don't know if I mentioned, maybe I missed it. Here we use the Hamming distortion, and this is just the frequency of binary error, number of bits in which we get an error relative to the length of the source sequence. So let me explain this here. So this is one description which is optimal, and it lands on the rate-distortion curve. It is designed in such a way so that it is positioned on the rate-distortion curve. But as we are getting more descriptions, we are actually improving our distortion. The distortion is getting smaller, but it's not. But we are getting less and less gain in terms of decreasing distortion, which is to be expected. So as a result of that, for small SNRs, we expect performance close to rate distortion curve, and for large SNRs, we have an obvious gap with respect to the rate distortion curve with this approach. So we call this approach Q approach because of this notation. And then we looked at another, okay, so as I said, close to optimal for small SNRs. The same thing happened if we optimally, if we take n descriptions of the Gaussian source and we quantize each one optimally. So for each of the distortion is an optimal description with respect to the defined rate distortion curve. So here I have, for example, n equal 4. With the first one, I land on the rate distortion curve, and with each next collected, I'm getting some improvement, but I'm getting far away from the rate distortion curve for the large SNR.
And CK there is the capacity of one of those M channels?
CK is the capacity of the instantaneous channel that contains K deterministic channels and N minus K erasures. N minus K erasures. Because we quantize the channel. For example, we take that the maximum capacity of the channel is 3. And we quantize it into 4. And so this is the capacity. CK is the capacity of the channel that has consists of K sub-channels that are completely error-free. Okay, so now, so practically here the message is Gaussian and the binary have the same behavior. For large SNR, they go away from the performance curve. Now, erasure.
I think when she compares certain capacity, which she then splits into parallel channels, and if she splits into 4 parallel channels, each parallel channel has a capacity divided by K.
Just the quantization.
If K is 4, then the capacity is whatever C.
You agree with it?
For example, you can say that on those channels, when you do the quantization of the channel, and you experience an erasure on certain sub-channel, it is actually you didn't do a good estimate on that one, and you experienced cliff effect on that one.
When you
I think what, go ahead.
go ahead.
I was gonna say what's confusing, at least to me, is you're describing kind of, so I think there's kind of a homework probably now to solve, right? Because you pass this X through a collection of parallel channels, and then you erase or some of them, or put errors in some of them, and then you use majority logic, and you have a channel from X to X hat, and I can do a rate calculation for that. But somehow that whole analytical exercise is completely separate from what you're actually doing to do the encoding in these streams. Are the two connected?
Yeah, it is. For example, for here to do this, you have to come up with a linear code so that you match each source sequence of the sequence of L bits, for example, with a code word in that code, so that
it has this kind
code
of
word, when you decode it, gets compressed into something smaller than L, which causes the distortion smaller than D.
Yeah.
I mean, there are codes like that, but they are fairly tough. Especially for the binary symmetric source, no, it's not a problem. Any random LDPC code that you just consider as LVGN, so you take the LDPC matrix to create it, would work. But for non-uniform binary sources, which we actually have to deal with, you have to create a separate code that will achieve that. And that's a problem, per se. It's not easy in linear time. You can always create a code so that you are decoding it by inverting the matrix, but it's not going to work for the instance chains. So, but I'm just presenting here simple ideas why and how we came to the actual design. And actually, only here you can see certain behavioral laws, what is happening if you are adding different descriptions. So let me just quickly go over another approach. It also contains multiple descriptions, but this time multiple descriptions are just disjoint pieces of the source sequence. In other words, they are negatively correlated as opposed to positively correlated pieces in the previous part because they contain the same source. So with this part, if you have certain channel capacity K over N, as illustrated here, so you're collecting K disjoint pieces, you're going to land somewhere here, and that curve behaves fairly well for large SNRs and worse for small SNRs. So the simple idea here is to combine those two approaches because of this different trend of behaviors for different SNRs. So the approach Q, where you have multiple descriptions, each optimal for bad channels, and you have disjoint pieces of original bit stream that are good for it. So if you combine that so that within each description you apply certain rate splitting to Q and E, so you decide what part of rate 1 over N goes to Q and what goes to E, it actually represents an optimization problem if you know the channel statistics and you know what is the part of your channel where you would like to perform well, actually closer to the rate distortion curve than any of those two separate approaches. And that's a simple idea that we started with, and that can be further evolve into many complicated things. But this is the essence of that. Here I'm just explaining, but I'm going to just make a mess after that, so I better skip that. So this is just an architecture of hybrid approach. No, I can go back to this, but obviously, you know, if you want. So here's a bit stream. You divide it into sequences of blank tab. So here's the sequence. It's punctured here because we don't want the whole rate to go into this into this uncoded stream. So out of those punctured bits, we are taking 1 over n fraction and putting it here, and then we are combining it with the optimal decoder that is designed for the rate x over n, where x is the rate splitting parameter. So this is our hybrid description, those two combined. Then we packetize it, and then we send it over the network. Of course, the network is lossy here, and you sometimes get the channel, get the packet completely because it passes all the checks and CRC, whatever. So you got the packet. Sometimes it gets delayed or you don't get it. So it's a typical erasure network. Of those that you got, you split them according to the header here into, again, this disjoint piece of the punctured sequence here, and here you do the majority logic decoding. Of course, the error due to majority logic decoding is here decreased due to those additional symbols that you receive. And this is also P asterisk is, of course, a function of x because we designed our binary symmetric channel to be for 8x over n. So there's here an optimization that needs to be formalized well. And again, this picture where we are trying to find the x that is going to get us where. So in terms of how we do the optimization, if you define the Shannon optimal Hamming distortion for some rate Ri as d Shannon I, so this is the point that is on the curve, on the rate distortion curve. And this is the point that we achieve with our hybrid approach. And we define this Gi of x as the gap with respect to the rate distortion curve for the rate I. Now, we can define the optimization as the minimization of a function f, which is nothing else than the average gap, if you know the channel probability distribution Pi. of course, again, it is quantized. The channel is quantized into n states. So with this minimization of the average gap, we are getting different results. For example, one I just played with that. For example, you have a channel that is better for high SNRs, but there's also heavy tail here for small SNRs. So what is the splitting, the rate splitting parameter? It turns out to be actually 0.05, which means that only a small portion of the rate you are assigning to the optimal encoder, and a lot of rate you are assigning to the just punctured bit stream, because you have a fairly good channel in most cases. So this is.
So what does that picture of the channel mean? I don't know.
So this is the channel description for when the channel is quantized to 100 states. This is like the maximum capacity of the channel. And so this is just the probability statistical description of the channel. The channel is most likely to be in this area. It's something I called folded Gaussian. I just used that because it was easy to create different curves. I first defined a Gaussian with a certain mean and variance, and then whatever is beyond, outside of this range, I folded back uniformly into that. So just for the purpose of illustration. And so here I have those different statistical descriptions of the channel, curves for the channel. So here for this, what is this color? I don't even know. Pink.
You don't know.
For this pink channel, you have almost uniform distribution. And in terms of magenta, so yeah, for the magenta color, you are going to have about 0.1x if you want to minimize the average gap. But if you are minimizing the maximum, then, oh, it's somewhere here, I have to, can't do it. So this is just, for different, just a simple explanation of the whole process, how you optimize it. If you have a description of the channel. Of course, here you have smooth curves, and it's fairly intuitive why you are doing this, why you are splitting the rate in the way you are splitting. But so
let's coming back. These are different distributions that you put on the first graph.
Different distributions, and the matching colors,
Right.
are the optimal splitting ratios. So for those 5 curves.
So one corresponds to, what's the x-axis?
This is the very small, see this red.
Oh, the 5.
Yeah, it just so the deterministic channel. So
So you want to split more with the green line, You split less, the more concentration you have.
You put more into optimal, yeah.
I think you split at different places, right?
Yeah. Well,
It depends where this peak is. This is almost deterministic channel, but it's at the high SNR. So no more, as you can understand.
You have to encode more than where the channel is.
I think the goal is to switch your regime depending on some certain threshold.
Yeah, because
So
you're
that
sending.
threshold moves based on the
It makes sense. You have to decode it.
But it's not so straightforward, because you also have, here it is, but for those others, it's not.
So the brown line and the magenta line are sort of relatively close, but for some reason the magenta line's threshold happens way further out than the brown star.
It's not way further out, it's just here, let me project it on that. But yes, I mean.
But is it? I mean, it sort of seems very sensitive to what it seems like.
But minimizing the maximum is even more sensitive. than the average, because you actually now follow the curve. But so this is only part of the problem, you know, what I presented here, because it's a very complex problem. And why we approach that problem is because, as I said, there is a current problem with video. There is also a huge divide between the communities, and you don't know what people are talking about. So at least some bounds, we wanted to start with some bounds and to create and with some trends. And but there are a lot of there is a lot of work after that. How do we put those boxes for Gaussian and binary into the current video processing stream? Because we believe that we actually filed a patent for this, that we can put a box into that without disrupting the current video processing stream in the encoder. Then challenges in implementation. As I said, we have analytical boxes for binary symbols that is just a binary symmetric channel. But how do you construct a code that achieves that? It's a different problem. What does it mean? If you are interested, if you have a binary, is there a, yeah. So if you have a binary symmetric source, and this is the Rate-distortion curve. For binary symmetric source, in order to land on this curve, you have to find minimum of the mutual information between binary random variable, uniform binary random variable x, and its reconstruction x, so that distortion is smaller or equals some peak. In other words, so you are optimizing the conditional probability of x given x so that it results in a minimum mutual information, and it has to satisfy this. If you denote with p asterisk the conditional probability that actually results in the minimum here in R of D, and you denote with p asterisk x hat the probability of the output of the binary symmetric channel that achieves this. Okay, so this is the output probability. This output probability for BSS is always going to be also binary symmetric, regardless of D. And for that, whatever code you take, a linear code, random code you take to implement this, is somewhere very close to here, because of the weight distribution of the random linear codes. But if you take non-binary symmetric source of some probability p, it is going to result in some conditional probability, conditional probability p asterisk that is going to result in a p other than binary symmetric probability of output symbols, output binary symbols. And for that, if you take the same code that you achieved Rate-distortion curve here, you're going to land here, but literally here, with such an error, because the distribution of binary symbol in the random codes is close to uniform, and you want something else. And so this is the actual problem, and a long-standing problem in a lossy source code. So there are a lot of problems here that I just couldn't put into the presentation that we would like to work on, but also, you know, bear in mind that all this rate distortion is pointwise. The performance bounds are pointwise, and we want scalability. So we have to somehow quantify our performance trade-offs. And you asked me about video codec. I have it in another distribution, in another presentation. So if you would like to see the actual blocks and where it fits, I can show that as well. But the problem here is also characterizing statistically DCT coefficient here at the output of a DCT transform, so that you can actually claim that you can put your block based on Gaussian distribution. And what are the further transforms and processing that you have to do so that that approximation can be fairly good. So a lot of, but these are things that don't interest me very much. I just want to justify that I can. No, it's practically signal processing. It's not. So I'm more interested in the creation of codes that would perform well and satisfy the constraint. And regarding the, I can show you the. Okay, so.
Have you put some thought into how to design codes?
Codes that, yeah, Serbian, I'm sorry. I'm used to.
School plus understand.
Okay, so you can see it even this way. So, usually, in any state-of-the-art MPEG and H264, H265 video, you divide it into blocks. And blocks are different sizes now in those standards to facilitate identification of motion vectors. And as I said, motion vectors is practically finding the sequence of those blocks that look alike, and so that you can compress it better. And so these motion blocks are not presented here, but they are in a loop around the transform coding. You're practically trying to get better and better memory identification, who's correlated with whom, and you are always putting it to the transform coding. So there's a multiple paths here, so that in the end you can be satisfied with what your compression looks like. But this is a standard piece, transform coding, which is usually DCT, because as opposed to Karhunen-Levy transform, it does not depend on the data itself. It is completely independent of data, but it performs close to optimal, where optimal is Karhunen-Levy in terms of concentration of energy in just a couple of coefficients, and in terms of decorrelating the coefficients. So here we have close to the correlated small number of coefficients. We can do some singular value decomposition like thingy, do some stuff so that we can get planes of Gaussian distributed data. So we either apply our box here, or we don't do it here. We proceed with A to D conversion, which is just a standard digitalization. And according to Liner zip, you know how much you're losing with respect to rate distortion when you're doing that. So it's not a problem. So you can skip this here, go through AD conversion, get the bits, because these are the real numbers. Get the bits, and here you can put our binary blocks. Of course, multiple descriptions. And for each description, you do that entropy coding, packetize it, and send it to the network. So it is actually feasible to do that. It's just a matter of who is willing to do that and measure the performance, and maybe somebody is. But I would like to concentrate more on the boxes, on how to create codes. For Gaussian codes, it's even worse because you have to use lattice codes. But even at this level, but at this point, you would be able to stay this far away from the rate-distortion curve. I know what distortion I can get with respect to. Of course, there's always a problem with distortion, defining the distortion metric.
So when you say multiple description, you're really not doing multiple description. You're just sort of mimicking multiple description. Because, you know, in your model, it looks like you're simply taking X and repeating it. It's like essentially sending it over parallel channels.
But that's a multiple description of the same source.
So if you have multiple description, then you would have compressed information and not the same on each one of them. Then you wouldn't do majority logic. You cannot do majority logic if you have multiple description.
You can do majority logic if you do the trick bit by bit, like I did, passing everything to the analytical description of that, to a binary symmetric channel. But if you do the actual code, then you are not doing majority logic description. Then it's a problem. What is the actual optimal joint decoder? And you can use some Wiener zip there because you have side information in the decoder. So a lot of problems are opening once you define the small, simple problems. It's not. Does my answer satisfy you in terms of? Because here, for the binary source, if I have a binary source X, for example.
Multiple description means that somehow you compress X into different sort of, and then you put different stuff for each one. That's what usually means. But what you're doing in that picture, you're just repeating X on each.
On this picture?
No, on the picture where you describe.
But multiple description is describing a same source in different descriptions. I'm adding independent noise to that.
You're having
adding different instances of the, if you want,
you're having independent quantizers.
Yeah. The quantizers are independent. This is the same. That's why it's multiple description of the same source.
Okay.
But here it's I am capable of doing majority logic because I'm just using the analytical description of the optimal. But if you put that in a code word, then it's not that. It's some. You can create a typical decoder easily, but not the constructed one.
I think I understand now what you mean by multiple description.
So, well, I feel as if I'm, I didn't explain it all now, but
No.
It's a friendly environment, that's why I came here to practice. You can ask.
So there is the tar and the feathers in the same line.
We're trying to be friendly.
Yeah, I know.
Yeah.
I was suspicious of this for a long time when I started working because of the lack of consistency in the literature. You have to somehow relate Shannon's results to what people in multimedia are doing, and it's not easy. Or you relate physicality argument or optimal coding when, how can you put that in a box? So, that's it. Oh, okay, I'll have to
Switch to the other presentation.
With the full distortion results.
Here, there.
Yes, I guess I missed the part. What is the?
Which one?
The one with the next one.
The next one?
Yeah. So This is in the channel statistical description. What's the?
This is the
what's
PDF.
x-axis?
This is just the x-axis is K. This is
Okay, so number
screen of
channels.
my MATLAB.
What is K?
K is the current channel capacity, K over N.
Convention.
Because N is 100, so the current channel
this
is
is the-
K over N. And this is the PDF of that, just as a histogram. This is how I have some GUI that I created that is just creating different channels, and so I'm looking to at where the minimum is for the gap function that I define, whether it's average, maximum, or some other function.
So the minimum, the gap means 1 over n.
The gap is this is the Shannon.
No, I mean the optimal description by splitting.
So it's 0. This is x. This is the rate splitting. So it's 0.05. So only 0.05 over 100 rate goes to the optimal description, to the BSC. In the case when, you know, it's concentrated like that, which is not completely intuitive to me. And the rest goes to factored disjoint, to uncoded symbols.
Optimality means the optimal the rate-distortion curve.
Yeah. So this is the rate distortion from the curve for the rate Ri, for the rate I over N. And this is the distortion that we achieve with hybrid. If we take X, and the optimal X is, you know, so got from the
the x the plot with the green curve, the y-axis is
the y-axis is just the function of the gap, average gap.
Oh, maybe this function that you are.
Yeah. It's function. So just I wanted to illustrate somehow possibilities.
She has offered you a probability that this many channels will be working.
Or you may have a conditional probability as well. I'm also trying to do that.